So you may notice a lot of these look kind of familiar. So basically what I've done is sort of gone through our previous workshops and sort of pulled some questions out and changed them around a little bit, but it's sort of like, you know, the same basic idea. So you remember long ago when we were wee tots, we started doing unit conversions, and it's still going to be a thing. So here is a unit conversion problem, sort of fairly typical. Anyone tell me what this particular unit is?
Centigram?
That is centigrams. And so what is a centigram?
One gram is equivalent to 100 centigram. 100.
Excellent. That's right. So usually I just start these by just writing down what we have. And then what do you suggest the first unit we change?
Centigrams to grams.
I mean, that's what I would do. I mean, I'm not saying you have to do that, but that's probably what I would do whenever I have some unit that's like less than one, and another and then another unit that's greater than one. I find if I try and do the conversion directly, I will sometimes make a mistake. And that, you know, either I'll multiply them together wrong, or I'll divide one by the other, or I'll screw something up. So I usually stick to, yeah, finding a common unit between the two of them, which would be grams in this instance. So we want grams on the top, we'll put centigrams on the bottom. So what's my conversion?
1 gram to 100 centigrams.
And then what's my next conversion going to be?
Grams to kilogram.
So how do I do that? How do I set that up?
Kilogram at the top. Grams, 1,000 grams at the bottom.
That is correct. Because, yeah, remember, we always want to leave the unit we want left over. We want that on the top. We're generally going to cancel the one that's on the bottom. So I cancel my grams. And this also helps me see if I'm left, I check and see whether I've done each of these conversions properly. So 100 centigrams to 1 gram. It's really easy sometimes to do the 100 grams over 1 centigram. That's a really easy mistake to make. So I sort of just double check that one more time. And I'm left with the unit I want. So that's good. So what do I do with these two numbers? Because I've got scientific notation. I've got scientific notation over here, but I sort of have regular notation over there. What would you suggest we do about that?
We can also convert them to scientific. Or just put like 10 raised to the power of 2 and 3.
Yeah, there you go. Yeah, so this is 10 to the second, and this is 10 to the third. So if I multiply those together, I get 10 to the what?
5.
10 to the fifth. Right, so basically, I'm dividing this by 10 to the fifth. And so what would my final answer be?
$7.156 times 10 to the 6th.
With,
Kilograms.
there you go. Right, because remember, a number is just a number. Without a unit, it's kind of useless. Right. So, excellent. Let's do the next one. So we got a mole conversion. Boy, we're not going to have to do that very often, are we? So where do we start with this one? I want to end up with moles of water.
You can put what you have, so 6.0 times 10 to the 2 power of 2 grams. And then you do times 1 mole of water over 18.015 grams.
So 1 mole, 18.015 grams. So what number is this? What is that number? How many grams is that?
$600.
600, right. But I'll get to that in a minute. All right, so what's my answer? My first attempt at an answer here.
Is it 6.0 times 10 to the second mole?
But-
Over. Uh-huh.
Well, I still have to divide by 18.015 grams. So
33.30.
33 point, yeah, that's what I got too. I got 33.306 moles. So that's the unit that's left over. So how many significant digits should I report for this?
2.
2, right. So that's why I did this at the beginning, because if I put 600, how many significant digits are in that number?
1.
1, right? There's only 1. Only the 6 is significant. And if I did this, how many significant digits are in this number?
3.
3, that's right. So the only way to show 600 with 2 significant digits is to use scientific notation. It's the only way I can think of anyway. So if one of our numbers we're using has 2 significant digits, how many does the other number have?
5.
5, right. So how many do we use at the end? I've got 5 here. Is that okay?
It should be 2 only.
Should be 2, right? Because I'm multiplying or dividing. If I'm adding or subtracting, it's a whole different matter. If I'm adding or subtracting, then I have to look and see how many digits there are past the decimal. So if I was adding these two together, I could get 10.002. I have 5 significant digits, even though this one only has 1, because I'm adding or subtracting. When I'm multiplying or dividing, I'm basically stuck with the accuracy of whatever is the least accurate number. In this instance, it's my 600 grams of water. Okay. Let's do the next. Oh, come on now. Ooh, this is a fun one. Okay, so we've done the pressure of a bike tire before, but now I've changed it into something truly bizarre. So I want to go from pounds per square inch to milligrams per cubic centimeter. Why anyone would want milligrams per cubic centimeter, I have no idea, but let's do that. So we will start as usual. Here's my number that I want to convert. So where do you suggest we start? What unit do you want to change first?
I converted the pounds to grams and then from grams to milligrams.
Right, because that you want to use the conversions on the test sheet. Those are the ones available to you. And so we have a conversion of grams to pounds. So what's the conversion? Oops.
1.0000 pounds equals 453.59 grams.
No, 1 pound equals 453.59 grams.
Yeah, that's what I said.
Oh, okay.
But in the worksheet, it said 1.0000.
Oh, I see. Right, so we'll put grams on the top and pounds on the bottom. So 453.59 grams per pound. So that gets rid of my pounds. So what's the next thing to do?
1,000 milligrams over 1 gram.
Right, so I want to change those grams to milligrams, and there's 1,000 milligrams in 1 gram. So that gets rid of my grams. And then what's the final conversion?
1 inch equals 2.54 centimeters. Exactly.
Right, but how do I do the conversion if
Oh.
it's cubed?
You have to put you put inches on the top, and then you put 2.54 centimeters on the bottom, and then you have to do that 3 times.
What do
So
you mean?
inches times over 2.54 centimeters, and then yeah.
Well, basically it means I have to cube both the
Yeah.
top and the bottom. The whole thing. And that's the classic mistake that people make. They'll change inches, 1 inch equals 2.54 centimeters, thinking that 1 inch cubed is equal to 2.54 centimeters cubed, but that's not true. It's 2.54 cubed. So we have to make sure that we cube this number. So after all of that, so that gets rid of my inches cubed. So inches cubed are gone. And let's do a quick check of what units are left over. So what's left over is milligrams and centimeters cubed. So I think we should be good. So what final answer do we get? See if your math agrees with mine. So anyone have a number?
I got a 3064149.
That's what I got. Yep, milligrams per cubic centimeter. I got the same thing. So what's our final answer? How many significant digits should we have in this number?
Four.
But there's only 3 significant digits there.
Oh. Wait, but I thought that one was infinite though.
It's exact.
So it's an infinite number of significant figures.
That's correct. That's right. What about this one though? This only has that only has 1 significant digit, doesn't it?
It's not too small though. I would think you'd use whatever is on that 110.7.
Yes, but we have to
Before.
justify that.
Oh,
So this is justified because that is exact. What about this one? What about that number? There's how many significant digits in 1,000 milligrams per gram?
wouldn't that also be exact too? Because 1
That's
gram.
right. That's right. That is also exact. That's a definition. That's also exact. So that's also an infinite number of significant digits. So that's fine too. And here we have 5 significant digits. So we're good. So you're right. We should use 4 significant digits. So how do we use 4 significant digits to represent this number? So here's our 4 significant digits. How would I write that? I guess there's like 2 ways I could write that.
One is we could convert it to scientific notation.
Okay, what would my answer be then?
Uh, 3.064 times 10 to the 2, 3, 4, 5, 6. -6, I think.
No, plus positive 6.
Oh,
Yeah, that's a large number, not a tiny number. You could also give this number. That would be fine too.
oh, okay.
That also has 4 significant digits. Yeah. Excellent. All right, so going to have to use your table here, your periodic table, to figure these ones out. So first one, I have an ion with a +2 charge, an atomic number of 56, and a mass number of 139. So how do I write an ion with this information in it? What's the first thing I want to write down?
What the element is.
Mm-hmm. And how do I figure that out from this information?
What the atomic number is. It's 56.
56.
Or you could use actually what the mass number is too. That kind of works.
No, you couldn't use the mass number.
Oh, you couldn't?
Nope, because there's some elements have the same mass.
Oh, I see.
Yeah. But the atomic number is absolutely, that is the number that's absolutely unique for every element. So what is
Barium.
56? Barium. And the symbol?
Ba.
Ba. So I write down Ba. And where do I put the rest of the information?
Is it 58 on the top and 56 on the bottom? Bottom left and top right, top left.
Where am I putting 58?
The top left
Why am I putting 58 there?
to indicate the charge number.
No, the charge is 2.
Oh. I thought you would have to write whatever to indicate like how many protons there are, that kind of thing.
Well, what number, how many protons does it have?
58.
Nope. If it had 58 protons, it wouldn't be barium anymore. It would be, what would it be? It would be, where's 58? Oh, damn it. I don't have it. I don't have it on my particular.
Would it be cerium?
I took off the lanthanides on mine. It would be a different element altogether. So this is the number of protons it has. That defines an element.
I thought
The
that would,
56 goes at the bottom left, right?
Right. So you could either, so actually you don't have to do that because you've already indicated how many protons it has by doing what?
Writing the element.
Writing the element, exactly. So it's not strictly necessary, but if you are to put 56 there, generally we use that when we're doing elements that are decaying because of radioactivity. So radioactive decay releases one of the things it releases is alpha particles, which has a mass of 4 and 2 protons. And so we'll do that. So we'll have both the protons on the bottom and the mass number on the top, just so we can do the calculations. But when you're not dealing with radioactive decay, this isn't strictly necessary. So if you want to put it there, that's totally fine. If you don't want to put it there, or put it there, don't put it there, it doesn't really matter. We only use it basically for atomic decay. We're not doing that here. So this would be optional. But there's 2 more things we need to write down that are not optional. And what are they?
the +2 charge.
Yes, where do I put the +2 charge?
On the top right.
Top right. Oops. Yep, so we put it right there. And then, so that takes care of my charge, my atomic number. I still need the mass though. Where does the mass number go?
Top left.
Top left, right. So 139. So how many neutrons would this particular ion have?
$83.
83. Right. Yeah, we just take the that's the number of protons plus neutrons. That's the number of protons. We just subtract them and we get 83. Yep. Now, what about number 2 here? I've got 25 electrons, 26 protons, 30 neutrons. Where do I start by figuring out what element it is?
26 protons would make it iron.
Sorry?
26 protons would make it iron.
Iron. Right. So what's the symbol for iron?
Fe.
Fe for ferrous. So where's my charge? Where's my atomic mass? So if you wanted to put the atomic number in, you'd put it there.
Is it +1 because it's 25 electrons?
That's right. So it is 1 fewer electron than protons. These are positive. These are negative. So it's 1 more positive charge. So we just put plus there. Now, what would be its atomic mass?
It's the-
56.
Sorry?
Is it 56?
56, right. So in the nucleus where the mass is, we have 26 and 30. So 56.
So we don't have to put +1, just the plus sign's fine.
Yeah, either way, just plus or +1. Either one is fine. Yeah, in fact, I mean, I used to do that instead of 2+. And then I
And-
sort of, then I got out of that habit.
do you have to write the 26? Because that in the previous example for A,
No.
you said it wasn't needed.
No, you don't have to.
Oh,
Yeah. All right, last one. Again, it's an ion. Atomic number 33, mass number 75, and a -3 charge. So where do we start with that one?
So 33 is arsenic.
Arsenic. Oh dear.
And it's
So what's
AS.
AS? Mhm. It's not AR because what's AR?
argon.
Argon.
Argon, right. And what ions does argon make? Got very quiet. So if you were to see an argon ion out in the wild, what would its charge be?
Can it have a charge because isn't it stable?
Yeah, you're right. It doesn't have it. It doesn't make ions. Just seeing if you're paying attention. Yeah, it's a noble gas, doesn't make ions. So we have an arsenic ion here. So where do I put the rest of my information?
-3 at the top right.
Mhm. Then remember, you always want to say what isotope it is. If you're given the isotopic information, you have to include that as well. So where do we include the number to tell what is an isotope anyway?
Isn't it the neutrons is a different number from its atomic number?
You're
Like the protons
close.
and the neutrons are different in terms of the how much.
Right. The protons are the same, so it's the same element. The number of neutrons is different. So the mass is different, but the charge, the overall charge is the same. The number of protons is the same. Right. So where do I put that information to tell us what isotope of arsenic is it?
Is it 75 on the top left and 33 on the bottom left?
Right. And again, the 33 is not required if you're not doing nuclear calculations.
I'm just wondering what makes like barium acetate so deadly for us?
It isn't.
Really?
Sodium acetate?
No, barium acetate.
I don't think it is.
Oh, really?
I don't know.
Because I remember someone kind of dark.
I don't know. I don't think, no, barium. I don't think barium is. No, because when you're getting your colon imaged, you drink barium, and because it's heavy, and so they can image your colon as it passes through. So I don't think it's particularly dangerous.
Oh, okay, because well, there was a case where barium acetate was used to kill her father, and she stole it from her chemistry class.
I don't think it was. You sure it was barium?
Yeah.
Not. Yeah.
She
I
put it in
don't.
food, and then they thought it was like a food poisoning or something. But
Yeah, I don't. Well, I'll look that up. I don't think that's dangerous though. We'll check that.
and I'm curious about arsenic. I know arsenic was used initially as rat poison,
Yeah.
but it's definitely deadly for us. So I was curious in terms of like the mechanism why it would be deadly. I know it damages your like inner linings for your like your intestinal walls, And if you ingest too much, I know that I think you can have like your hair, it can be indication or something like that.
Yeah, you can find it. Yeah, it's a particularly, if you want to get away with murder, it's a particularly bad one to use because it's really easy to find.
Is there a specific mechanism as to why it's so deadly for us?
Yeah, I think it just shuts down the respiratory chain,
Oh, okay.
I believe. So speaking of isotopes, here we have a calculation where we need to figure out what the average atomic mass is. So how do we figure out what the average atomic mass is? And what does AMU mean?
Atomic mass unit.
And
Right.
what's that equivalent to?
Is it what the atomic mass is? Or is that like the percentage?
Well, AMU, yeah, I mean, it's atomic mass units, but it's basically equivalent to grams per mole. Basically, it's the same thing. It's the mass of each individual proton and neutron. But it's basically equivalent to grams over per mole. So how do I do a calculation like this? So I've got these abundances. So it means like around 81% of this particular atom weighs 40, around 5% weighs 41, and around 14% weighs 42. So how do I get the average
We
mass?
convert first.
Hmm?
So all those percentages should equal 100%.
Okay, do they?
So yeah, I believe so.
Okay,
And then you
I know I
convert,
cheated. I made them up myself.
and then you convert the those percentages,
Mhm.
and then you're gonna multiply.
Convert them to what?
You're convert them to decimals.
Okay,
So
so
you
what would
take
80.92% be?
0.8092.
Right. Right, because all percent means percent in French just means per 100. So we just divide all those numbers by 100, and that gives us the fraction. So what do I do with that fraction?
You're gonna multiply that by the number that is associated with the AMU.
The mass associated. Okay. So 39.99. Okay.
So you get 32.359908 for the first one,
35.
or 32.
Oh, 32. Sorry. I did this earlier. So yeah. 32.3599. Okay.
Then same thing for the other ones. So 5.26 divided by 100 is 0.0526.
Mm-hmm. 40.99. What does that give me?
2.156074.
674.
074.
Oh, 0. Okay.
And then same thing for the last one, 13.82 divided by 100, 0.1382. And then multiply by 41.99
Mhm.
is 5.803018.
0.803. What's the 0.803 what?
018.
018. Okay. So this is, so when I add these up, that's going to give me the average, is it?
Yes.
Okay, so so add them up. What
40.
do we get?
40.319.
Keep
So
going.
we need AMU.
Why
and
did you stop at those numbers?
because that was the whole number when you calculated it, but then you still need to do, I think, is it 4 significant?
What about
digits?
all these numbers here? You didn't use those?
When I put it in my calculator that was online, that's just what it gave me.
Oh, I see.
Yeah, that was an exact number it gave me.
I see. Oh, it was exact?
Mm-hmm. I don't know. I think I used the one that you gave us on the website. And that
Oh.
was the exact number that popped up.
Wow, okay. Let's
It
see,
was
let's see,
either-
let's see if we should use that then. Yeah, when I added them up, yeah, I got it like a 0 there. So need to figure out how many significant digits we should use. So how do we do that?
I think the smallest one is 5.26%. So that's 3 significant figures.
Okay, so this number, the number we use to calculate that should have 3 significant digits. So where are my 3 significant digits in that number?
Is it 40.3?
Nope, no, I'm asking for this number right here. How many significant digits should it have? You said 3, right? Because there's 3
Yeah.
digits here. So where should I cut off my digits with that number?
2.15.
Yes, exactly. So anything after that is not going to be significant. Now, that does not mean you should round it to 2.16. That doesn't mean that at all. You never, ever, 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 ever round your numbers before finishing your calculation. So we do not do that. So what we do is we keep that as a 5. We do all of our calculations, and then we see where our final answer should be rounded. And it looks like it should be rounded 2 digits after the decimal. And we'll just make sure of that. So this number, the first number, has 4 significant digits. So that also should be right there. And this one also has 4 significant digits. That would be to there. So our final answer should have 2 digits beyond the decimal point. So what would our final answer be?
I have a question about that.
Oh, sure.
So we're looking at significant digits already in the solutions from getting the percentages. So don't we just add up all the numbers and then look into the answer?
Right. Yeah, that's what we did. We used all the digits. We use all the digits we want to do the calculation. But then at the end, we have to figure out how many significant digits should be in our answer.
Oh, so all you're doing is just comparing.
Right. So now I'm seeing
Oh, okay.
how many significant digits should the first number give us, the second number give us, and the third number give us. And the first one gives us 4 significant digits. So here's our 4. 1, 2, 3, 4. The second one gives us 3 significant digits. 1, 2, 3. And the third one gives us 4 significant digits. 1, 2, 3, 4. So that tells us that the most we can go beyond the decimal point is 2 places. This one goes by 2, this one goes by 2, and this one goes 3 beyond the decimal. So we have to chop it off at 2 beyond the decimal. So that would be right there.
Oh, so
What-
we don't look at the problem, we look at the solutions that are given or what we've calculated.
Well, we have to look at the problem to determine how many significant digits each number will have. Like, there's 4 there, and 4 there, and 3 there, and 4 and 4, and 4. But since we're multiplying and adding, we take into consideration significant digits from the multiplication. So we have 4 for this one, 3 for this one, and 4 for this one. But now after that, we're adding. And so the rules for significant digits change after that. Then it's a question of how many digits beyond the decimal point do you go? When you're
Okay, I see.
adding and subtracting, there's different rules for significant digits. So what I'm saying is you do all your calculations first using as many digits as you like, because that'll give you the most precision. But then when it's time to give the answer, you have to determine how many significant digits you are to report.
I have a question for average. I always thought averages, you add all of them and then you divide it by 3. But in this case, for average atomic mass, you don't do
Okay,
that.
that's
do
an
you?
excellent question. How come we can't do that here? Why don't we just take 30, 40, 41, and 42 and divide by 3? So it should be 41, right? Why is it less than 41? So why can't we just divide by 3? Anyone want to help her out?
They have different AMUs.
Nope. Nope, that's not the reason we can't divide by 3.
Because of the different percentage abundance.
Right, they're not equal. They're not equal in number. If the atoms were equally distributed, 1/3 of them were 40 and 1/3 of them were 41 and 1/3 of them were 42, then yeah, you could just, or you had 1 atom each, then yeah, you just divide by 3, but we don't. We have like a huge number of atoms, and 81% of them are the lightest kind. So that skews the average to it being lighter. They're not there in equal amounts, is why we can't divide by 3. Yeah, for other times we're calculating averages, we're actually adding up individuals. We're not dealing with individual atoms here. We're dealing with large numbers of them. That's why we can't divide by 3. So what's my final answer after all of that?
$40.32.
That's right. But you're not 40.32. You'd lose a point for that.
AMU.
That's right. 40.32 AMU. Because now that we know we have 2 significant digits past the decimal, then we round this number. So we can see that it's right next to a 9. That's bigger than 5, so we round it to 2. Excellent. Man, yeah, we had a lot of good conversation with that one. We haven't talked about that in a while. Okay, so we want the name of these compounds and the Lewis structure, as well as the shape. So this first one, I've got 1 nitrogen and 3 chlorines. So what would I call that?
Nitrogen trichloride,
Why wouldn't I just call it nitrogen chloride?
because there's 3 chlorines.
Yeah, but if I had like iron chloride, I could just call it iron chloride, iron 3 chloride, couldn't I? Or
The
iron.
covalent bond.
Ah, that's right, because it's covalent. It's not ionic. Excellent. So who goes in the middle for that one?
Whichever one is the lower electronegativity, which would be nitrogen.
Nitrogen. It's not much lower than chlorine. It's actually pretty close. So I got my chlorines around the outside. How many total electrons should be in when I put my 1 bond, because they all going to have a single bond at least. How many total electrons should this have?
Nitrogen can only have 5.
5 total electrons?
5 valence electrons.
Valence electrons, right. because we're interested in what are valence electrons?
They're on the outermost shell.
And what do they do? To the outermost electrons, that's absolutely right. And what's the purpose of them? What do they do exactly?
Those are where the bonds happen, like the
Right,
covalent bonds?
exactly. Those are the electrons available for bonding. It doesn't mean all of them are going to be bonding, but those are the ones that are available for bonding. Right. So nitrogen is 5. How many does chlorine have?
7.
How do we know that? What's the quickest way to figure that out?
Group number on the periodic table.
Right. Nitrogen's in group 5, chlorine's in group 7. That's the number of valence electrons in their outermost shell. So we got 3 chlorines, that means 21. So we got 26 total electrons. So how many electrons do we have left to put around this structure?
20.
20, right, because we've used 2, 4, 6, so I got 20 left. When you have electrons left over, where do you put them? Where do you start putting them?
Go around the chlorines.
Yeah, around the outside, just like the old do-si-do. You go around the outside. So we got 20 to get rid of. So we go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 18, and I have 2 left over. So where do they go?
So it's a lone pair on top of nitrogen.
Yeah. So if there's any left in, you put them in the middle. So to check that, the easiest way to check is to sort of, if you know what atoms generally look like when they're binding. So nitrogen generally looks like this, right? Since it has 5 valence electrons, it's normally sharing 3 of them to make bonds and keeping 2. So how many total electrons does nitrogen have here? What's the number it's trying to get to?
8.
It's trying to get to 8, right? The magic number is 8. Everybody wants to have 8 electrons in their outermost shell, and they'll either share electrons with somebody else to get them, they'll give electrons away to go down to 8, or they will steal electrons from someone else to get to 8. So in a covalent structure, we add the shared electrons and the lone pair. So it's got 2, 4, 6, 8. So it's happy. Does it have a charge in this situation? How would we know whether or not it should have a charge? Because 8 seems like too many, right? I thought you said it only has 5. So would that have a -3 charge on it? Yeah, how do we determine whether these atoms are charged or not? Man, it got real quiet.
If there's more than 8 valence electrons?
Nope. So it still has 5 valence electrons. How do we know it still only has 5 valence electrons in this structure? It has a total of 8. So it's, if you add together the electrons it keeps to itself and the electrons it's sharing, it is a total of 8. But it still only has 5 valence electrons. How would we count them? So if we're using nitrogen as an example, I'm claiming it still only has 5 valence electrons in this model. How would you prove that?
You don't count them as like a double, so it'd be the 2 on top and then 1 on each side.
What do you mean by 1 on each side?
Like it's the one that's closest to the end. It's not going to be, you're not counting it as like 2, 4, 6. It's going to be only 1 of the
So
pair.
yeah, basically you only count 1 of the bonding electrons in each bond, right? So if we were to count the number of electrons that nitrogen is actually bringing to the party here, the number of electrons it can claim as its own, it's only these 2, because that's a lone pair. That's not shared with anybody. So those are nitrogens. And it brought that one, and that one. So basically you count half the bonding electrons and then the lone pairs. And so it is a total of 2, 3, 4, 5. So there's no charge on the nitrogen. What about the chlorines? Do we get any charge on the chlorines? Chlorine should have 7 valence electrons. And how many do they have here?
You have 7.
Also have 7, right? So there's 2, 4, 6 in lone pairs. Those are all chlorines and nobody else's. And this one gets to call that one of its valence electrons too, because it's doing bonding. So you count the electrons doing bonding or that it's keeping to itself. So chlorine also has 7. So there's no charge in this molecule. How do we determine what shape it is?
You look at your chart.
That's right. Which chart?
Uh,
The axe.
The Axe body spray chart, right. So what does A stand for?
the arrangement.
That's lovely. I wish that was true. It's the atom, central atom, because we're looking at from the viewpoint of the central atom. So around the central atom, there is both X's and E's. What do the X's refer to?
Are
I
those
think
the
it's-
bonds?
Sorry?
I know one of them means lone pairs.
Right. Which one is which one do you think is lone pairs?
E.
E, lone pairs of electrons. Right. So how many lone pairs of electrons does remember the central atom? We're only dealing with the central atom, A. So how many lone pairs does the central atom have?
1.
1, right? So, and then what does X stand for?
The bonding groups.
Yeah, basically bonding groups, bonding regions, basically means how many atoms is the central atom bonded to. So how many bonding regions, bonding groups, bonding atoms is the nitrogen attached to?
3.
3, right? There's 1 here, 1 there, 1 there. So then we just look up AX3E1. And what is that?
Trigonal pyramidal.
Yeah, trigonal pyramidal. And what that means, whenever you have 4 regions, it means you have a pyramidal shape or pyramidal shape. So in 3 dimensions, it would look like this. So you'd have your nitrogen, and then you'd have a chlorine coming out, a chlorine in line, and a chlorine going behind, and then the lone pair on the top. So basically, it would look like there'd be nothing above, and then 3 chlorine atoms slightly below. So it sort of look like this. That's what it would look like. Okay, let's do the next one. Oh, go
I have a
ahead.
question. So on that chart where it has like the tetrahedral
Mhm.
on top, is that like a main category?
Yes, that means that all the shapes in there start as a tetrahedron.
So we don't have to name tetrahedral, we just can name trigonal pyramidal, and that's fine.
Right. Right. So in this instance, this would be our nitrogen would be here. There's the chlorine, there's the chlorine, there's the chlorine, and there's the lone pair. But it also is the same shape for methane. But it looks different because methane has a hydrogen there, a hydrogen there, a hydrogen there, and a hydrogen there. So when you're looking at the actual shape of the molecule, you don't see the lone pair. So this is going to look like it's just 3 atoms sitting below the plane. This looks like a pyramid, but they come from the same shape group. The only difference is this has an atom and this has a lone pair. So we want the shape of the actual structure, not the group that it's in. Yeah, so we would want, so this would just be called a tetrahedral, and this would be called trigonal pyramidal. Although, yeah, they both come from the same 4 electron regions group. All right, let's do the next one. And let's finish 4, then we'll take a little break and then come back and finish up. So let's do the next one. So I've got, what do we call this?
Xenon difluoride.
Xenon difluoride. But I thought that's a noble gas. I thought noble gas can't form compounds. Is this possible? Is it possible to make this compound?
They're special. They're special.
Who's special?
The
I'm
the noble
special?
gas
Thank you.
ones.
What's special about it?
The xenon.
What about xenon?
It could break the rule, the octet rule.
Yeah, I can break the octet rule, but it's still a noble gas. Can it actually form covalent structures, covalent molecules?
Is it because of the halogen?
It's because of fluorine, right? It's not just any halogen, it's because of fluorine. So neon does not form compounds so helium does not, neon does not, argon, I think the jury's still out a little bit on that one, and xenon and krypton can. So no, don't know yet. Yes, yes. What's the difference between these 2 noble gases and these 3? How come these 2 can make compounds and these can't? or don't so far.
Isn't it because the row is past like row 3, so it's like row 4, row 5?
What does that mean, row 4 and row 5? That's right. This is in the
There's
first
more
row.
than
That's in the second
32, I
row. That's in the
believe,
third
right?
row, fourth.
There's more than 33, I believe, that
But what difference does that make, though? I mean, you're onto something. It's on a low. It's lower down on the periodic table. What does that mean?
Does it have something to do with our electronegativity?
Not really. A little bit, but not really. Because remember, electronegativity can only be calculated in a covalent bond. Electronegativity, no atom has an electronegativity by itself. It has to be bound to something else, and it's the relation. It's the electronegativity is basically a relative thing. So we don't say that helium basically has no electronegativity. Neither does neon or argon. Krypton and xenon do, however, because they can form compounds. So it is indirectly related to this electronegativity. So if these are in the first 3 rows, and these are in rows 4 and 5, what's different about these two? They still have 8 valence electrons. Neon is 8, argon is 8, xenon is 8, krypton is 8. But what's different about them, these two? As you go down the periodic table, what happens? Every time we add a row to the periodic table, what are we actually doing? We're adding another something.
Is it adding another energy level?
That's right. We're adding another energy level. We're adding another shell. So helium is only 1 shell. Neon has 2. Argon has 3. Krypton has 4. Xenon has 5. So every time you add an energy shell, what happens to the atom?
It becomes more stable.
No, not really. Something happens to it, though. I'm just going to keep doing this.
It's like you add another you can add more electrons.
It has more electrons. You have more energy levels. You have more shells, and so the atom gets
bigger.
bigger. Exactly. The atom gets bigger. And as the atom gets bigger, the nucleus in the middle has less and less pull on these electrons spinning around it. So the pull that the nucleus has on this electron is relatively strong because it's close. If it's way out here, it's less. It has less pull on that electron. So something like fluorine comes around and it has extremely high electronegativity. It's so high, it can pull electrons away from noble gases. But those electrons have to be really far away from the nucleus, so the pull is less. So it can't do it to helium because those electrons are way too close to the nucleus. And it can't do it with neon because those electrons are really close too. But by the time we get out to krypton and xenon, those atoms are huge. And so the pull on those outer electrons is much, much, much less. And so fluorine can grab one and form a bond with xenon. All right, did some learning there. So how many, so actually we can make xenon difluoride. I think we can make xenon tetrafluoride too, I think. And maybe even hexafluoride. I think that might be pushing it though. So how many, so we'll put xenon, which one's going to be in the middle? I guess we already know it's going to be xenon in the middle, right? Because fluorine has a higher electronegativity than everybody. So I'll put a fluorine there, a fluorine there, and at least a single bond. So how many total valence electrons should that molecule have? How many does xenon have?
Eight,
Xenon has 8, right? And what about fluorine?
7,
7, and there's 2 of them, so that's 14. So that's 22 electrons. So how many like lone pair electrons are there going to be?
Three.
3,
Sorry? So we have to subtract the number of electrons that are in bonds. So how many are in bonds right now?
4.
4. So we have 18 electrons left. So where do we start giving them?
go around the fluorines first.
Yep, fluorine to go to the outside first. So fluorine has 7 valence electrons. So they're going to get 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 12. So I got 6 left. So where do the other 6 go?
So you get 3 lone pairs around xenon.
Right. So 1, 2, 3, 4, 5, 6. So let's check and make sure that everybody is the right number of electrons. So does the 2 fluorines, do they have the right number of electrons? They have 7 valence electrons and a total of 8.
Yes.
They do, right? They have 6 lone pairs, and they have 1 in the bond. So they have 7 valence electrons. So that's right. And they have a total of 8 because they're sharing 1 with xenon. So the fluorines are cool. What about the xenon? Does it have the right number of valence electrons?
Yes.
It does, right? 2, 4, 6, 7, 8. So the xenon is cool as well. So everyone's cool. Everyone has the right number of valence electrons. Xenon has more than 8 total electrons, though, doesn't it? How many total electrons does xenon have? It's got 8 valence electrons, but how many total electrons does it have? So for total electrons, we count all the lone pairs and all of the bonding electrons too.
Then
It's got 10, right? 2. It's got 6 in lone pairs. Oops. 6 in lone pairs. And it's got 1, 2, 3, 4 in bonding for a total of 10. So that's more than 8. Should it have a -2 on it? Is it negatively charged?
Yes.
Okay, anyone disagree or agree?
I thought the -2 wasn't needed because just based off of what we explained with how xenon is row 4 and with fluorine being so electronegative and everything, you didn't need to do that.
Yeah, but it's still, well, that just explains how it can make bonds. It doesn't explain whether it having 10 total electrons gives it a charge or not.
So do we add it because you should only have at most 8 in each?
Are there elements that can have more than 8?
Yes.
There are, right? What elements are those? What do you need to be in order to violate the octet rule?
I believe a halogen, right? For the most part.
No, halogens really don't violate the octet rule. Well, they do with no, that's not true. Iodine does. Iodine will. Bromine will occasionally. But what do you need to be in order to violate the octet rule?
Be at row 4 higher.
Row 3 or higher. Yeah, so you got to be in row 3 or more, because you have to have space to put them in. So like, for instance, oxygen is in row 2. It can only have a total of 8. Sulfur is in row 3, and so it can have more electrons than 8. But so xenon having 10 is not a problem because it's a big element. It's in row 5, so there's plenty of room in the outer shell to put more than 8 electrons. But does it have a charge of -2 if it has 10 total electrons? How do we calculate charge? Do we use total electrons to calculate charge, or do we use valence electrons to calculate charge?
Valence.
Valence, that's right. So we don't use total electrons because sometimes, like sulfur can have 12 electrons and phosphorus has 10 electrons routinely, but they're not charged. So we have to figure out how many valence electrons xenon has. And how do we calculate valence electrons? It's different from total electrons. So here, xenon has 10 total because there's 2, 4, 6. That bond makes 8, and that bond makes 10. But how many valence electrons does it have?
8.
Where do they come from?
The periodic table.
No, well, yes, the periodic table, but how does it have, we mean in this particular structure, does it have 8? How would we determine that?
Yes, because you're counting the single valence electrons that are around it. So there's
So which
6.
ones are valence electrons for xenon? Which
The
ones
3
are
lone
valence
pairs.
electrons?
The 3 lone pairs.
3 lone
are-
pairs, right? We start with the lone pairs because basically what valence electron means is those are electrons that belong to xenon and no one else. So we start with the lone pairs because those are definitely xenons and nobody else's. So 2, 4, 6. So where are the other 2 valence electrons for xenon here?
One from the bond with fluorine.
Right. So when we're counting total electrons, we count all the electrons that an atom is both sharing and being shared with. So basically all of them. So fluorine has a total of 8 if you count that shared electron and that shared electron. But as far as valence electrons go, fluorine just counts 2, 4, 6, and this one. because it's holding on to one that keeping for itself. It's basically the one that it brought to the party. And xenon is the same way. We count all the free electrons, the free lone pairs, but only half the bonding electrons. So that's 6 for xenon, 2, 4, 6, and then that one makes 7, and that one makes 8. So it has 8 valence electrons in the diagram. It's supposed to have 8 valence electrons, so there's no charge.
I remember on the periodic table something about on the right side,
Mhm.
it's like 0, and then the charges are negative, like as it increases as you move to the left.
Right, as you go to the left, you go from all the elements on the right side of the periodic table are non-metals, and non-metals generally take electrons from metals. So when they form ions, they're almost all negatively charged. But the noble gases don't make ions. They don't ionize.
So like in the case of fluorine, it would have a -1 charge then,
If it was an ion,
right? If it was an
Yeah.
ion, okay.
if it was an ion, because when it's an ion, fluorine has 1, 2, 3, 4, 5, 6, 7. And when it's an ion, it takes another electron to give it 8 total, so it's stable, but it has 1 more electron than it normally does. And so it has a -1 charge. So fluoride ion is really, really stable because it's really, really small and it has 8 total electrons. And so it's very stable. So xenon has no charge. The fluorines have no charge. So let's get down to the shape. 1, 2, 3, 4, 5, 6. So I go to my Axe body spray. So my central atom is xenon. So X is what?
Two.
X is 2, right? X stands for how many bonding areas, bonding groups, or really how many atoms is bonded to the central atom. And there's 2 fluorines, so that's 2. And what does E stand for again?
How many lone pairs?
Right. Now, lone pairs total, or lone pairs on the fluorines, or lone pairs on the xenon? How many lone pairs?
on the xenon.
Right, just on the central atoms. How many is that?
3.
3. So we look up on the magic table, AX2E3, and what do we get?
Linear.
That's a linear molecule, right? So if you were to draw it, it would look like this.
And for the final, we don't need to draw it, right? But
I
we
might
do
ask
need
you to
know.
draw it. So you'd have a lone pair coming out of this, a lone pair behind, and a lone pair in plane with a fluorine on top and a fluorine on the bottom. So if you were to look at it, just remember, you don't see the electrons because they're too damn small. You would just see a linear molecule. All right. CS2. Who goes in the middle?
Carbon.
Carbon. Carbon always goes in the middle, pretty much. It's very rarely that carbon does not go in the middle. So we have carbon on this side, put an S on this side, S on that side, single bonds. So how many total valence electrons should we have here? How many does carbon have?
6.
Carbon is 6?
4.
4, right, group 4. Sulfur has 6 for a total of 12. So I should have 16 I've got 4 in bonds. So I have 12 left over. So where do I start putting them?
To the sulfur.
On the sulfurs, right? 12. So I go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and I'm done. So let's calculate charge. So how many valence electrons does the carbon have in this particular structure?
It only has 2.
It's only got 2. Poor thing. Yeah, it's only got 2. So does carbon have a charge?
I thought carbon always has 4.
It should, but in this instance, it's only got 2. So would it have a charge?
Yes.
It would. What would the charge on carbon be?
That's 2.
+2, right. Now let's look at this sulfurs. So how many valence electrons do the sulfurs have?
Seven each.
How many? So how many
7.
valence electrons do the sulfurs have?
7 each.
7, right. They have 3 lone pairs for 6, and they're sharing another one. So that's 7. So do they have a charge?
Is it -1?
Yes, they each have -1 because they have 7 electrons and they're only supposed to have 6. Oh, other way around. So their charge is -1. So I've got a -1 charge on the outside and a +2 in the middle. And what's also wrong with this picture? Not only is there charges present, but what else is wrong? What else is wrong with the carbon?
It doesn't have enough valence electrons.
Doesn't have enough valence electrons, but what else?
It's also not fulfilling the octet rule.
There you go. Yeah, it's also way behind on its octet as well. How many total electrons does carbon have? We saw it has 2 valence electrons, but how many total electrons does it have?
Just 4.
It's got 4, right? It's sharing 2 bonds. Each bond is 2 electrons. So the total number of electrons that carbon has around it is only 4. And it should have how many?
Should have 8.
Should have 8. It's an octet rule. It's all about the octet. So it should have 8. So not only the fact that we have sort of unnecessary charges on this issue, but carbon doesn't have enough electrons. Sulfur does have enough electrons. Sulfur has 8. Sulfur's happy. Sulfur has 8 total electrons. It's got 3 lone pairs, and it's got another 2. It's got a bond, so it's another 2 electrons. So sulfur's happy. Carbon's very sad. So how are we going to deal with this situation?
Where we create double bonds.
Yes. How do we do that?
So you take 1 electron, valence electron from each sulfur.
Okay,
And then,
so I go.
or
one,
sorry, the pair, you give one pair.
Take the
sorry,
pair, right,
one
you take
pair
both of them. And you make
and
another
Another
bond.
bond. Mhm.
You take these two, move them there, make another bond. So now we have this. Now, does this work out for everybody? What's the charge on carbon now?
Now it's 0 because it's happy. It's got 4.
Right, it has 4 valence electrons now. So there is no charge on the carbon. What about the sulfurs? Is there a charge on them?
Same, it's happy because it needs 6. So there's
It has
2 lone
6, right,
pairs.
and it's got 6, so there's no charge. So now there's no charge and everybody is 8 electrons, so everyone's groovy. So what do we call this thing? What's the name of the compound?
Carbon disulfide.
Carbon disulfide, right. So it's carbon disulfide, and what shape is it going to have? So I got my AXE. So sulfur is not the central atom, it's carbon. So I'm looking at what's around carbon. So X, what's X going to be?
Two.
2. It's bonded because there's 2 bonding regions. It's bonded to 2 atoms. There's 2. And how many lone pairs does carbon have?
0.
0. And that's usually the case. There's very, very rarely does carbon have a lone pair. That does not happen very often. Like in carbon monoxide, it has a lone pair. Cyanide ion has a lone pair, but not very often. So AX2. So we look up AX2. What do we get?
It's just linear.
Linear, right? Just a linear molecule.
For the X2 part, how do you look at it? Because I don't know, the way I'm looking at it, it looks like there's 4, but maybe I guess I'm
4
looking at it
what?
wrong. 4 pairs.
No, X stands for the number of bonding regions or atoms that are bonded to the central carbon.
So it's
There's
not
only-
considered 4 because the double bond is considered 1.
Yeah,
Okay.
yeah. If it's a double bond, a triple bond, a single bond, it doesn't matter. It's basically how many atoms are bonded to the atom in the middle.
And then for the E part, you said it's 0. But I know so far there's still some
Yeah.
lone pairs
But we're
here.
dealing only with the central atom. So X stands for the central atom. It should be CXE, but I guess, that would make more sense. But so X stands for like the number of atoms that are bonded to the central atom, and E is the number of lone pairs the central atom has.
Okay.
So outside the central atom, there's going to be lone pairs all over the place, but those don't affect the overall shape. They may change the angle slightly, but they're not going to change the overall shape. So carbon almost never has a lone pair. So this is a linear molecule. Is it going to be polar or non-polar? Is it a polar molecule or a non-polar molecule? Who's more electronegative, carbon or sulfur? I'll tell you, it's
I
sulfur.
believe it's sulfur. Yeah.
Yeah. So if I was to draw a bond dipole from carbon to sulfur, who would it be pointing at, carbon or sulfur?
Carbon will be pointing at the sulfur, right?
It'd be pointing at the sulfur, right? So the carbon would be slightly negatively charged, slightly positively charged. The sulfur would be slightly negatively charged. And the same is true in this direction. So is this a polar molecule or a non-polar molecule? I have 2 polar bonds.
Non-polar.
It's but the molecule itself is non-polar. That's right. Why is that?
Because of the equal pooling.
Right, because these dipoles cancel each other out. They're equal and opposite. Each of these is exactly the same size because the difference in electronegativity between carbon and sulfur is the same in this direction as it is in this direction. And they're opposite because it's a linear molecule. So they're pointing in exactly the opposite directions. So when you add them up, they cancel each other out. So it's just like carbon dioxide. Carbon dioxide is also a nonpolar molecule. It's a gas. So carbon disulfide is also a gas at room temperature. Excellent. Let's do last one and we'll take a little break. So I've got sulfur and 6 bromines this time. So who's going in the middle?
Sulfur.
Sulfur. And I'm going to have 1, 2, 3, 4, 5, 6. So is this allowed?
Yes, because
How come I don't? Oh, go ahead.
BR is a halogen, and I
Mhm.
believe it's after row 3, right?
Sorry.
Is it at row 3 or after it?
Does it matter that bromine or sulfur is beyond row 3? I could easily make this fluorine, it would still work. So who's making, bromines are only making 1 bond, sulfur's making 6. So it's more important to decide if sulfur can make 6. Can sulfur make 6 bonds?
There's 6 valence electrons. So
Right.
I believe it could.
But what does it need to be in order to make more than, so it'd have a total of 12 valence electrons. Is that allowed?
Yes, because bromine is more electronegative.
No, that's not the reason. What is it about sulfur that allows it to make more, have more than 8 total valence electrons? The fact that bromine's more electronegative means those bonds will be polar. That's correct. But what is it about sulfur that allows it to make 6 bonds and have 12 total valence electrons? Why can it do that? So oxygen is just above it in the periodic table. Oxygen's also in groups, in group 6. It cannot do this. So what's the difference between oxygen and sulfur?
Sulfur is in level 3.
Oh, right, sulfur's in the 3rd row. So when it's in the 3rd row, did we talk about S, P, D, and F? I can't remember. The orbitals? Did we just briefly touch on them?
Yeah, we talked about it.
Okay, yeah, so S has 2 electrons, P has 6 electrons, D has 10 electrons, and F has 12. No, sorry, 14 electrons. So in the first row, you only have 2. Second row, you have 2 plus 6. Third row, you have 2 plus 6 plus 10. You have room for 18 electrons in your outermost shell when you get to the 3rd row, because you're adding all these new orbitals. So sulfur can violate the octet rule and does all the time. So it can, so that's not a problem. So next, we need to decide. Oh, and the other reason when we don't put bromine in the middle, how many bonds does bromine make typically? How many valence electrons does bromine have? We need to figure that out anyway. So we got sulfur and we got bromine. How many valence electrons does bromine have?
Seven.
7, right. So since it has 7 electrons, how many bonds does it normally make? How many electrons is it trying to get?
1.
It's trying to get 1 more, right? Everyone wants to get 8. Everyone wants to get to the magic octet house. So if you got 7, you only need 1 more to get to 8. So bromine and all the halogens generally only make 1 bond. So we don't normally put halogens in the middle. They're almost always on the outside. The only time they're not is when they're bound to another halogen, like fluorine, for instance. Fluorine can steal electrons from if it can steal electrons from xenon, it can certainly steal electrons away from like iodine or even bromine. But generally, the halogens go around the outside because they're usually only making a single bond. So if bromine's making 7 and there's 6 of them, that's 42 electrons, man, a lot of electrons. How many valence electrons does sulfur have?
Six.
6. So there's a total of 48 electrons. And how many are in bonds right now?
12.
12. So that means there's 36 left. So I'll put those around the outside. And basically, that puts 6 on all 6 bromines. And then sulfur doesn't get any. So does everybody have an octet now?
Yes.
Yes, they do. All the bromines have octets because they have 6 valence electrons, 6 lone pairs, and another 2 in a bond, so they're good. Are there any charges on this molecule? Because we certainly know sulfur's got more than an octet. Sulfur's got 12 total electrons, so it's not complaining. What about charges, though? Is there a charge on the sulfur?
No,
How come?
because it has 6 valence and 6 bonding. So
Right, it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. So it's got its 6 valence electrons, so it's good. And the bromines have 7 valence electrons, so they're good. So everybody's good. There's no charge, and everyone has, in some instances, more electrons than they need. So what would the shape of this thing be? What is my AXE for this one?
so X is 6.
I got 6 atoms
Mhm.
around the sulfur. And how many lone pairs does the sulfur have?
0.
None. So we look up AX6 and what do we get?
Octahedral.
Octahedral. Wow. So what that would look like is you would have sulfur in the middle, and with 1, 2, 3, 4. So these would be coming out. These would be going behind. And then you'd have a bromine on top and a bromine on the bottom. So this would make sort of a square shape around the middle. And then basically you'd have like two pyramids stacked on top of each other. So quite a, now would that be polar or non-polar? Non-polar. Basically, anytime you see a molecule that's completely symmetrical, it's going to be non-polar. So, and if it's not symmetrical, it's probably going to be polar. So that's basically how that works. So why don't we take like a little 5-minute break and go tuck everybody in, and then we'll finish off, okay? Give everyone a chance to get a breathe or something. So I'll be back in a sec. 5 minutes. Oh, okay. Now that we're back and I'm freezing to death. So mass percent composition. What does that refer to? Mass percent. If I wanted to know the mass percent of silver in that particular molecule, how would I go about figuring it out?
Is that the solute mass over the mass of the solution?
But it's not in a solution. I just have a solid here. Yeah, generally, yeah, mass, one of the meanings of mass percent is, yeah, how much of a solute is in a solvent. That's right. But here, I just have a solid, presumably. I just have a formula. So what is it referring to? Percent composition of silver. What do I, first of all, what do I call this compound? What would that be called?
I was actually wondering, the previous problem, you didn't name the compound. SBR6,
Oh, okay. What would it be
Um,
called?
is it hexabromide?
Yep, sulfur hexabromide. Yep. So what do we call this one?
Silver phosphate.
Why not trisilver phosphate? So which one's right? Trisilver phosphate? Silver 3 phosphate? Or just silver phosphate? Which one will we call it?
Isn't it the 3 came from the phosphate group?
3 comes from the phosphate group. So what do you mean by that?
I think it's the charge of the phosphate group.
Right, so the phosphate group does have a charge of -3. That is correct. So what's going to be the charge on the silver? What's always the charge on a silver ion? It's always the same.
+1.
It's always +1. Yeah, it's one of those weird transition metals that always is the same charge. So what do I call this? So that means I have 3 silver ions to balance with +1 to balance the -3 charge. So I need to have 3 of these. So that's the formula, but what's the name? So it's either trisilver phosphate, silver 3 phosphate, or just silver phosphate.
Is it silver 3 phosphate?
Okay, why would you call it that?
Because of it being a transitional metal, right?
But what does the 3 stand for when we're referring to a transition metal? Does it refer to the number of ions, or does it refer to the charge on the ion?
Isn't it the charge?
It's the charge. And what's the charge on the silver?
1.
1. So that doesn't work. So what about trisilver phosphate? That works, right? Because there's 3 silvers.
Aren't transitional metals similar to metals in the sense of you don't need to label how many silver there are?
Well, you always have to tell in the formula, you always have to say, you mean in the name or in the
In the name,
name, right? So
Because
why don't we have to
phosphate-
say it in the name?
because phosphate, you already know it has -3, right?
Right.
So you
So
would
do
know
we-
that iron would have to be +3 in order to balance out the 2.
Right. So do we do silver 1 phosphate then?
I thought it was just silver phosphate.
It is. So the reason we don't use silver 1 phosphate is because silver is always +1. That's one of the rare. It's silver, zinc, and aluminum. Zinc is always +2. Aluminum is always +3. And they make a little ladder on the periodic table. So yeah, so this, because it's ionic, you don't say how many atoms are in it. You just give the charges and let people figure it out for themselves. So if it was sodium phosphate, you would just assume that there had to be 3 sodiums with +1 to match the -3 of the phosphate. You don't have to say how many there are, because there's only one way you can put those things together. All right, so mass percent composition. Where do we begin? Just, we really still haven't defined what this means. So it's the percent of silver out of what?
Is it the mass of silver over the total mass?
That's exactly right. Yeah, it's basically, if I had 100 grams of silver phosphate, how many grams of it would be silver? Is what we're asking. So how do we figure that out?
So compute for the molecular weight of silver phosphate.
Okay, how do we do that? Other than looking it up. We actually had to calculate it, which we do. How do we do that?
A good old periodic table.
Yep. So we're going to need the mass of silver. We're going to need the mass of phosphate, and we're going to need the mass of oxygen. So what's the mass of silver? Silver's pretty big.
So silver is 107.868 times 3.
868 times 3. Okay. And phosphorus is 30.974. And oxygen is 15.999 times 4.
So the total of the silver is 323.604.
323.604. Okay. And that's 30.974. And this one is
63.996 grams.
63.996.
Total load.
What's my total?
418.574.
418.574 grams per mole. So that's the total mass of silver phosphate. What's my mass of silver in it?
One oh seven point eight six eight.
I'm sorry?
So 107.868.
Mm-hmm. Is that the total mass of the silver in the molecule? Because remember, we want the mass of all the silver in the molecule
Times 3.
times 3, right? So it's this one. We already have the number. So how do we calculate the percent composition?
Just divide 323.604 with 418.574 times 100.
574. And then what do we do after that? Because we want to
Multiply
match
by
percent
100.
times 100, right? Because we want a percent. So what's our answer?
77.3110.
Actually, it's this, right? So how many significant digits should we report? That's percent. Because we're not given any other numbers. We're not told, like, how much silver or anything. How many significant digits can we use here?
Do we just use 1 because of the 100?
Nope, the 100. Nope, the 100 is not considered a part of it because that's just the conversion factor. We're just converting a fraction to a percent. So we don't consider that. That's exact.
Is it 5?
Why 5? Because of the phosphorus?
Yeah.
Nope. You're close. How many significant digits are there in our mass of silver?
6.
6. And how many significant digits are there in our mass of the silver by itself?
6.
6. So we're dividing something that has 6 significant digits by another number that has 6 significant digits. So we actually could report this to 6 significant digits if we wanted to. So 77.3111%. That would be the actual answer you could give. So basically, it's how accurate is are your masses. Since we're dealing with masses with 3 digits past the decimal place, that gives us a lot. If you were only dealing with masses like 1 past the decimal place, then we'd have far fewer significant digits. All right, those numbers. Oh, number 6. This one will go pretty quick. All right, number 6. So which ones are ionic? And which ones are covalent? So what's the difference? What makes an ionic compound different from a covalent compound?
Is it the metals, metal and non-metals?
Right, ionic has
Ionic?
ionic is metal and a non-metal. What about covalent?
Is both non-metals?
Yeah, both non-metals. That's not always true. I don't want you to think that's always true, but generally, like 99% of the time, that is correct. Really, it's based on how the electrons are shared. But in general, we'll just use the rule that, yeah, almost all the time, ionic compounds have a metal and a non-metal in it. So what would that be? Can even draw it for you.
Would that be ionic?
Why?
Because the iron is a transitional metal.
Where's there an iron?
Oh, sorry. Never mind. I read that for some reason I read that as Fe.
No, it's fluorine.
I meant covalent actually.
Yes, that's covalent. What about B? What's Ru? What do we call that?
Ruthenium?
Ruthenium, that's right, excellent. So what would we call that compound?
Is it ruthenium oxide?
Is that enough information?
Ruthenium dioxide?
No. Why wouldn't it be ruthenium dioxide? We wouldn't call it that, actually. Why not?
Is it because it's a metal and a gas?
Well, not a metal and a gas. It's a metal and a non-metal. So does that make it ionic or covalent?
Oh, it's ionic.
That one's ionic, right? What would be the name of it though? We can't call it ruthenium dioxide because that's what we would call it if it was covalent, but it's ionic. So what would we call it? You can't call it ruthenium oxide either, because that's not sufficient information. We have to be able for the person we're describing it to know that there's 2 oxygens. But it's ionic. So we can't use the dioxide. So how do we give the information that there's 1 ruthenium and 2 oxygens?
Is there like is it like a Roman numeral or like
Yes, you use the Roman numeral. exactly. Which one would we use here? What would the charge in the ruthenium need to be in order to balance the two oxygen ions? Remember, this is ionic, so these oxygens are going to have charges on them. What is the charge on oxygen when it's an ion?
-2.
-2, that's right, because it has 1, 2, 3, 4, 5, 6 valence electrons. So when it's an ion, it picks up 1, 2 more. And so it's -2. So if there's 2 of them, what must the charge on ruthenium be?
Is it 5?
Would that balance out the 2 oxygens? So then I'd have 5 and 2 -2s. That would give me a charge of +1.
Should be 4.
4, right. So the charge on ruthenium is 4. So how do we make that plain from the name of the compound?
So ruthenium 4 in parentheses.
That's right. So we would go ruthenium 4 oxide, because it's a transition metal. So we have to, and it can vary its charge. So we would say ruthenium 4 oxide. Excellent.
So to determine the charge, you said because it's a transition metal,
Mhm.
then is it always a -2 charge?
Oxygen's always a -2 charge. Yes. So oxygen's always -2. The halides are always -1. Nitrogen's always -3. Phosphates their phosphorus is always -3. Sulfur is always -2. Yeah, they're always the same, because they always have the same number of electrons in their outermost shell, and they always arrange them in the same way. Whereas transition metals can arrange them in a lot of different ways in order to maintain stability.
It's
So,
not-
oh, go ahead.
Oh, sorry. It's not it's not, you won't write ruthenium brominobutyl 2 oxide.
No, why would you do that? Because that means the
Um,
ruthenium would have a +2 charge. So if I
I
had,
guess I was thinking because, oxygen is usually -2.
right, but there's 2 of them. There's 2 oxygens, so the total charge
I
from the
see.
oxygens
Okay.
is -4. So we need to balance both of them out, not just the one.
Okay.
Yeah, if it was RuO, then it would be ruthenium 2 oxide. Yeah, then that would be correct. So what about number C? Letter C. Ionic or covalent?
Covalent.
Right, there's no metals there. So what would we call that?
Nitrogen triiodide.
Triiodide. Yep. And D. There's one we don't see very often. I thought I'd throw some curveballs in there because we haven't dealt with these elements. What's W?
Tungsten.
Tungsten, right. Tungsten is super dense. It's even denser than lead. Some people are saying we should use tungsten bullets instead of lead because they don't poison wildlife. So sounds good to me. Anyway, so I've got tungsten and I've got bromine. So is this ionic or covalent?
Ionic.
Ionic, right. What do we call that? Tungsten is a transition metal. What are the charges on bromide ion?
It's a -1.
Right, it's a halogen, so it's got 7 in the outermost outermost shell. So it just needs 1 more, so it just steals 1. So each of them will be -1. So what must be the charge on tungsten be?
So it's a +5.
+5. So what do we call it?
Tungsten, Roman numeral 5. Bromide.
Bromide. Yes, you got it. That would be the name of it. Mhm.
So it's the group number that we're subtracting from the charge from the group number
To figure out what's the
to
negative
figure out
charge.
what the charge is on the first element. That's what I'm trying to figure out.
Right. Yeah. So the first, you always put the metal first. So the metal goes first, and then the non-metal goes second. And the nice thing about the non-metals is we always know what their charge is going to be. So it's either going to be -3, -2, or -1. So all the group 7 are all going to be -1. Group 6 are going to be -2, and the group 5 are going to be -3 because they all want to get to 8. So then we can always figure out what the charge of the metal is based on what the charge of the non-metal is and how many there are. So if there's 5 times -1 for bromide, then we automatically know if there's only 1 metal, then it's got to be +5. So then we would call it tungsten 5 bromide. If it was 3 bromines, it would be tungsten 3 bromide. Yeah, luckily we don't have transition nonmetals there, then it would just get incredibly difficult. But the nonmetals are somewhat more well behaved. So what do we call E? What would that be? Covalent or ionic? What's K stand for?
Potassium.
Metal or non-metal?
It's a metal.
That's a metal. So ionic or covalent?
Ionic.
That's ionic. So what do we call it? What's Se?
Selenium.
Selenium, right? Very good. So what do we call the ion of selenium or selenium, depending where you're from?
It's a -2 charge. Oh, where we
Right.
at?
It is a -2 charge because it's in group 6. It's right below sulfur. So what's the name of it though? So if sulfur is sulfide, what do we call selenium? You don't hear it very often. So I take off the and what do I replace it with?
Selenide or
Selenide. Yep. Just put "ide" at the end. So it's selenide. So we potassium selenide. So is it potassium 2 selenide, potassium 1 selenide? What do we call it? Is potassium a transition metal?
No,
It's Alkali.
That's right. It's an alkali metal. Excellent. Yeah. So we just call it potassium selenide and we're done. Because potassium's always +1, selenide's always -2. Always, always, always. So we don't put any numbers in the name. Now, F. Ionic or covalent?
Covalent.
Yep. There's no metals, right? There's just sulfur and oxygen. They're about as non-metal as it gets. So what do we call that?
Is it maybe sulfide? I know SO4 -2 is sulfate. So
Is this an ion or is it a compound? So is there a charge in this?
It's a compound.
Why is, well, how do we know it's not an ion?
Because didn't we say they're both non-metals?
So, sorry?
They're both non-metals.
Well, non-metals can make ions, right? They make polyatomic ions. I mean, Vera is right. SO3 can make sulfite, but is it sulfite or is it something else? Sulfite is the ion. So is this an ion or a compound? And what's the difference between them?
Is it because they both have a -2 charge?
Mm,
Like would
do they
it
have a charge in this?
cancel?
Do they have a charge here? Or don't they? I mean, you just said it was covalent and that was correct. So does that mean there's going to be a charge on the molecules, on the atoms? I mean, there might be. But how do we know that that is a compound and not an ion?
Does it have to do with its polarity?
Mm, nope. Well, I mean, no, not really. If it was an ion, what would it have? What will we see there?
Negative charge.
A negative charge, right? Is there a negative charge shown?
No.
No, because if there's no negative charge, that automatically means it's a neutral compound. So that is not sulfite ion. Sulfite ion is this. There's no -2 charge there. And so it is not the sulfite ion. It is instead a neutral compound. And so what will we call it?
Sulfur trioxide.
Sulfur trioxide. Exactly right. All right, what about G? It's an element we rarely see because it's super, super, super rare. It's probably not enough of that stuff on the planet to blow your nose with. It's just really rare.
Francium?
Francium, right. So is this a ionic compound or a covalent compound?
Ionic.
Ionic, right. Francium is a metal. So what do we call it?
Francium chloride.
Francium chloride. So do we call it francium 1 chloride? Do we include the Roman numeral or not?
No need because it's always +1.
Right, we don't because it's in group 1. So it's always, always, always +1 if we could scrape enough atoms together to make a compound. It's really, really radioactive. So it's, yeah, it's really rare. Now this is an interesting mu. What do we call? What is that? What's MO? What element is MO?
Molybdenum?
Molybdenum. Yeah, I have trouble with that one too. So is that a metal or a non-metal?
A metal?
That is a metal. So we have an ionic or covalent compound.
It's ionic.
That's ionic too. So what would we call it? Is molybdenum transition metal or not?
Is it, it's a transition metal?
Oh yeah, it's a transition metal. So what would be the name of that compound?
So is it molybdenum 5 oxide?
So if it was 5, so molybdenum would be +5 and the oxygen
Oh,
would be,
Sorry, I used the wrong one. It's
what's the charge on the oxide ion?
-2, so
-2.
it should be 4.
So if molybdenum is +4 and oxygen's -2, I still have a charge of, there's only 1 oxygen there, not 2. So I still would have a overall charge of +2. So what must the charge on molybdenum be? There's only
Plus-
1 atom of each one, right?
+2.
Got to be +2, right? Because oxide, there's only 1 oxide ion and it's -2. So molybdenum must be +2. So it'd be molybdenum 2 oxide. Now, last one. I have, so this might be a little confusing. I have 1 iodine and 3 chlorines. So ionic or covalent?
It's covalent.
Covalent, that's right. 'Cause they're all non-metals. In fact, they're all halogens. So what would I call this bizarre thing?
Is that iodine trichloride?
Mm-hmm. Yep. All right. Yeah. Getting down to the last one here. I saved the best for last. Because I know how much everyone loves these sorts of problems. Good old stoichiometry. Yay for stoichiometry. So I've got a question here concerning, oh dear. Oh, we're back. Concerning an amount of reactant going in, another reactant, and how much product is made. So classic stoichiometry question. So when you're doing a stoichiometry question, what's the very, very first thing you need to do?
Make sure the equation is balanced.
Oh yeah, very first thing. So is this equation balanced? Because on the final, I'm not going to tell you whether or not the reaction is balanced. So if you assume it is, you may be making a mistake.
It's not balanced.
That is not balanced, right? So what's the first thing we should do? With combustion, there's sort of like a general rule of which you should balance first. So what's like the first thing we should balance? Do you remember the rule? Generally, with a combustion reaction, we balance the carbon first, the hydrogen second, and then the oxygen last. So, yeah, because carbon, basically, this carbon goes to one place, and just one atom of it goes to the carbon dioxide. That makes it fairly easy to balance. The hydrogen goes to only one place. It goes to water, but there's two of them, so it makes it a little more tricky to balance. And then the oxygen's sometimes very tricky because it goes to both products and in different ratios. So that makes it a little trickier. So we do the carbon first. So how many carbons do I have on the left side of my reaction?
3.
So how many carbon dioxides am I going to make?
You make 3 also?
Yep, just going to make 3 of them. And I told you the carbon dioxide part is generally pretty easy. And then what about the water? How many hydrogens do I have on the left?
8.
8. So how many waters do I need to balance that out?
4.
4, right. So that balances my carbons and my hydrogens, but I have my oxygens left. So how many oxygens do I have on the right side now total?
3.
On the right side. Oxygen atoms.
6
I got 6 here.
plus 4.
And then how many do I have in the water?
4.
4 more, right? For a total of 10. So I need 10 atoms of oxygen on the left side. So how do I do that?
Put coefficient of 5.
Right. Yeah, so the thing to not get confused by is that we're dealing with atoms here, not molecules. So I need to balance the atoms on both sides. So 10 atoms of oxygen is equal to 5 molecules of oxygen. So a lot of people make the mistake of put a 10 there and be all screwed up. Now, if you have an odd number of oxygen molecules, because you have like, you know, or if you have a weird number, let's say you have 13 oxygens and you need to put like 6.5 there. How do we deal with that? Because we can't have 6.5 molecules of oxygen. So what would we do if we had like a 6.5 or 5.5? How will we get all even numbers in our reaction? All whole numbers.
Can you actually repeat that?
So if I had, let's say, on the right side of the reaction, I had 13 atoms of oxygen. Because I made, you know, 6 moles of, sorry, 4 moles of CO2, and I made 7 waters. That'd be 15. So I had 15 atoms on the right side. So then I would have to have 7.5 molecules of oxygen on the left side. Well, I can't have half a molecule of oxygen. So how would I deal with that situation? It's late. I'll just let it go. We will just multiply everything by 2. Just multiply everything by 2. So I'd make that 14, I'd make that 8, and I just make that 15. Then everything would be a whole number, then everything would be fine. Here we have all whole numbers, so we don't have to worry about it. Sorry, it's too late to be doing stuff like that. Anyway, so now we have a balanced equation.
So
what's
first
our-
you look at the carbon, and then you look at the hydrogen
second,
and then the oxygen.
oxygen last. Yep.
Okay. And why do you go like that?
Because carbon is easy. It only goes to one location.
Okay.
Carbon just makes carbon dioxide. So that makes it easy to balance. And then all the hydrogen just goes to one place too. It just goes to water. It doesn't go anywhere else. The problem with the oxygen is that it goes to both. It goes to both products. So you need to have both of your products balanced before you can balance the oxygen. You need to know exactly how much water and carbon dioxide you make before you can balance the oxygen properly, because it makes both.
Okay.
Yeah, that's why. Yeah, I mean, you can do the hydrogen first and then the carbon, but you always do the oxygen last. So now we have a balanced reaction. What's our next step? Because we need to, what the question is how much water in grams is produced. So where do we start with such a heinous question? We can do this. We've only got one more to go. We can push through.
So we need to identify which one is consumed first,
So we need to identify which.
which is the rate limiting agent.
Oh, right. We need to figure out which is a limiting reactant. It's either we have excess propane, or we have excess oxygen, or we have exactly the right number of each. But of course, I'm not going to do that because that would be wrong. So one of them is going to be in excess. We don't know which one it is. So one of them is going to be limiting, meaning it will dictate how much product will be made, because once it's used up, you can't make any more product. So how do we figure out which one is limiting?
Compete for the number of moles.
Right, we need to figure out how many moles of propane and oxygen we have. How do we do that? So I've got 32.6 grams of propane. And I want to figure out how many moles that is. How do I do that?
You need to compete for the mass of propane.
Okay. So what am I going to multiply? So 1 mole over what am I going to put in the denominator?
The molecular mass of propane.
Right. And what's that?
44.097.
44.197?
097.
Oh,
gram.
097. Okay. Okay, so that gets rid of my grams. I'm left with moles. Now, is that enough information? Just knowing the number of moles of propane, is that enough information to tell me whether or not it's limiting?
Would you also need to do one where you convert the moles of propane to see how many grams of water you make?
Exactly. Yeah, just knowing the number of moles of propane really isn't going to help me very much. What I really need to know is how much water would that make? Or, and it could just be moles. If you just want to go to moles, that's fine. So I need to continue and figure out moles of water. That's what I want. How much product am I going to make? So where am I going to put moles of water and moles of propane in my next?
Moles of water is going to be on top.
Yes. So moles H2O on top and moles C3H8 on the bottom. So that gets rid of my moles of propane, and I'm left with moles of water, which is really what I want. And if I want it to go all the way to the end, I could convert that to grams, since that's the answer I want anyway. So I might as well just keep going. So if I wanted grams of water, what do I put on the bottom here?
Put 1 mole of H2O.
Right. So what is my ratio of moles of water to moles of propane? It's not 1 to 1.
Be 4 to 1. 4 H2O to 1 mole.
That's right. I go back to the equation. 4 to 1. So 4 there and a 1 there. And then how many grams of water are in 1 mole of water?
18.015 grams.
Oh man, 18 point. I don't think I used one that accurate. 0.015. Yeah. So that gets rid of my moles of water. And the only thing I have left now is grams of water. So how many grams of water? Now remember, this is using the assumption that I have all the oxygen gas I need. So that means if I converted all of this propane to water, this is how much it would make. So how much is that? So if every gram of propane was converted into water, how many grams of water would I be left with?
5.88302 grams.
Is it 5 or 53?
I got 53.1.
53.
Yeah, I think you just moved a decimal over. Yeah, I think it's 53.3. So I just used 3 significant digits because why? Why did I use 3 significant digits?
3 sig figs for the grams of propane.
Yep. So that's how much water I would get if I had more than enough oxygen and all the propane was used. And next, I do exactly the same thing, but with the oxygen gas. So then I just take want to convert that to moles, convert that to water, and then convert that to mass of water. So what's the first conversion I do with the oxygen.
1 mole of oxygen is equals to 31.998 grams.
Is it? I'm sorry, what number did you give?
31.998.
Oh, I'm sorry, you were right. Yeah, I was just about to say, remember, there's 2 atoms. Yeah, you already did that. So yeah, I'm not even, yeah. So remember, 1 atom of oxygen is 15.999, but you multiply that by 2, and so you get 31.998 grams. So that gets rid of my grams of oxygen. Then what's the next thing I want to do?
Moles of water over moles of oxygen.
Right.
And based off of the balanced equation, it would be 4 moles of water would over 5 moles of oxygen
Right.
gas.
Mm-hmm. So that gets rid of my moles of oxygen. And then I just finish it up using exactly the same 18.015 grams of water over moles. It gets rid of my water, and I'm left with the same thing. I'm left with grams of water. So everything else cancels out, and I'm left with grams of water. Now it's just a matter of figuring out how many grams that is. So how many grams do you get for water?
We got 47.922.
Yep. 47.922. Would that be your final answer? How many sig figs should it have?
Is it 4 because of the 106.4?
Yep, should have 4. So 47.92. So how much are we going to make? Which one is limiting?
The oxygen gas, right?
Oxygen's limiting, right? Because you make slightly less. So the answer would be 47.92 grams. I know some of you like to just get the molar ratio and then figure out how many moles of oxygen and how many moles of propane and then do some trick with the ratio. That's fine if you want to do it that way. I just find it easier just to figure out the whole thing at once. Actually calculate how much product I would get from each one separately and then do the comparison. But you can do it any way you like, as long as you show all your calculations, that's fine. So which reactant is in excess?
The propane.
Propane, right? So your propane is in excess and the oxygen is limiting.